An assembler will convert assembly language program to machine language. Now, to understand these assemblers and compilers, we have to worry about the type of machine for which the target code is made. Why? Because the job of assembler, translator, and interpreter or compiler, all these things they are generating some piece of code which is to be executed by the target machine. So target machines architecture is a matter of concern for the assembler designer and compiler designer. See, majority of the modern machines are built on stored program concept. There will be a memory in the computer system where program and data will be stored. Then, with the help of a control unit will go through the program code one at a time. Instructions will be fetched to the arithmetic logic unit. Arithmetic logic unit will do the necessary calculation. This concept is called as stored program concept. Here you can see that both the instructions and data will share a common bus. And that's a performance bottleneck also. At a time, only instructions or data both cannot be channeled. And this concept was proposed by Sir John von Neumann. Sir John von Neumann and his concept called as von Neumann architecture or Princeton architecture is a fundamental topic in computer science. This was proposed in 1945, and this model is still being followed in majority of the modern computers. There is one more model called as Harvard model, in which case programs and instructions will be having separate bus. And this model is being still in use. See, still in the era of AI, we are using a model that was proposed in 1945. So how relevant is his brain and his model? So the Almighty gives capacity for humans to think beyond centuries. And we see that we make use of those concepts even today. Based on stored program architecture, the internal architecture of a machine will look like this. There will be a main memory unit. There will be a central processing unit. There will be a control unit. There will be an ALU. And they work it together so that our program will be getting executed. We will just mention about few of these. See, location counter, we know it is just like program counter. What is program counter? Program counter is, it holds the address of the instruction that is to be executed in the next, and that is stored in the program counter. See here, instruction interpreter. You can see that it is a set of electronic circuits that performs the intent of instructions fetched from memory. This is very important. Fetched from memory. From which memory? From primary memory. And we know that since we know the concept of a process, we know that the program will not entirely, the entire program will not be loaded. The most requisite portions of a program will be loaded to the process. Then process will demand for more partial portions of the code as and when required. That is arrangement. Whatever it may be, that job will be done by the OS. As far as the code is loaded into the memory, from primary memory, each instruction will have to be loaded. Each instruction will have to be interpreted, and then the result will be computed. The sequence goes like that. For that purpose, there has to be a location counter. Location counter is also called as program counter. Program counter is a register which holds the address of the next instruction to be executed. It is an address. Why address here? Because the instructions will be kept in primary memory. When you keep something in memory, it will be having some memory location. So address within this within this address, we are here. So the contents will be there. Contents will be there looking at the address. So address is very important. This address will be kept in program counter. So program counter value will indicate to CPU which instruction is to be executed. And that is a job of LC. It's also called as PC and IC in different names for the same circuit, same register. Now next is IR, instruction register. A copy of location counter is also kept in IR. Now working register, memory devices that has served as scratch pads. Why scratch pads? See, we may have to add two values and there can be an intermediate value. Suppose that we have a big equation like b square minus 4ac. We humans, we know that we can compute simultaneously. We can substitute values for b, we can find out b square, we can also find out 4ac, we can subtract, we can arrive at a result. How does a computer does that? Have you ever thought about that? A computer cannot do b square minus 4ac in a single go. Instead, first b into b may be calculated, b square may be calculated. Then 4 into a into c may be calculated. Before that exercise, there is b. Value of b is a variable. That means value of b is kept in a place somewhere in the primary memory. From there, that value will be accessed. So there is a time for fetching some value from memory. So value of b should be fetched. Value of a should be fetched. Value of c should be fetched. Then b into b should be calculated. The intermediate value is to be kept somewhere. Then for a value of a into value of c into value of into 4, it is to be computed. There will be an intermediate value. Then these two intermediate values will be taken. Then it should be subtracted. Then the net result will be taken, and it should be returned. This is the way ALU works. So for that purpose, there will be a lot of working registers. Now, memory address register. It contains the memory location that is to read or to store into. From which values we have to read values, and from where to the values are to be stored back. What's meant by reading and writing? When you say that x equal to I, x is a memory location. You are writing to a memory location. When you say that I equal to y, you are taking a value from a memory address y, and you are loading back that to a value called I. So there are load and store operations. Addresses for these locations are to be stored. MBR contains a copy of the content of the memory location whose address is stored in MAR. Then comes the memory controller. Memory controller is a piece of circuit, is a part of the IC which will transfer the content of MBR into core memory. Core memory means primary memory. So content of MBR is to be transferred to core memory location, and MBR and MAR was in tandem each other. Channels will be used for data transfer. We have a bare idea of the architecture. Now we can move on to assembly language program. If you were to design an assembly language, assembler for an assembly language program, say it will be for a particular CPU, you should have sound knowledge on the machine architecture for which the assembler is being made. Every language will be having some alphabets. Alphabets will be grouped together to form words. And when we form words will be having some good composition, and based on that composition, we will be having statements. That is how we go with every language. So similarly, assembly language is also a language. It will be having a lot of statements. Now, what about assembly language? Assembly language, see, we know the classifications of programming languages now. We have high-level languages and we have low-level languages. Here, low and high means, are you closer to the architecture or closer to the user? So in the high-level language, it will be English-like. In low-level language, everything will be specific to the machine. So suppose that we want to add two numbers. We will say x plus y in CPP. We will say x plus y in CPP. What will happen? X plus y, when you express in assembly language, it will be add x and y. It need not be x and y. Value of x will be lowered to a register. Value of y will be also lowered to a register. Then we will add both. Either we will load one value to the accumulator. Second value will be kept in a register. Both will be added. Result will be kept back in the accumulator. So this is the way assembly language works. When you go up to machine language, the instruction for adding will be again a binary code. So x plus y, there is an underlying operation there, plus. For programmers like us, plus is enough. We know that when we say x plus y, it is addition. So looking at plus, when the compiler will generate, instead of plus, it will be an add instruction. Add instruction will be in binary. Value of x, again in binary. Y will be represented in binary. So everything will be expressed in binary format. When we go for assembly language, there will be mnemonic codes. Mnemonic codes are English-like codes. Assembly language program is still close to the machine. It is, we can say that is in between high-level language and real target language. It's a middle-level language, one can say like that. There, we will be having several opcodes. What's an opcode? Add, for example. Add may be an opcode. Load may be an opcode. So if you say in high level language, it can be x equal to 1. It can be I equal to 0. When this is translated to assembly language, it will be opcodes. There will be two kinds of opcodes, pseudo opcode and machine opcode. Pseudo opcodes are instructions assembler itself. We will know what is meant by this. There are some instructions which are specific to a program. For example, at what address my program is getting started. That is something, that is an instruction. So all these kinds of instructions are called as pseudo opcodes. So pseudo opcodes will be executed by the assembler itself for managing our code, whereas machine opcodes are instructions to the CPU about the program written by us. So there are two kinds of opcodes. So in assembly language program, we having these kinds of pseudo opcodes and machine opcodes. And when an assembler converts an assembly language program to a machine language program, he will have to worry about these codes. He should know how to handle pseudo opcodes and machine opcodes and to generate the corresponding target code. Now, here see the last statement, operands. What do you mean by operands? We know about that. Plus is a binary operator. A plus B, in that case, plus is binary. A plus plus, it is a unary operator. So there, in high level language, we know that operators will be having some operands. When we come down to say assembly language and say a target language, these opcodes will be having some operands. There could be opcodes without operands and with operands also. See this one example. In this part here, we have an assembly language program. So this is John start 0, and these are all the assembly codes. So we can see that here there are opcodes and machine codes. Opcode start is a pseudo opcode. It is a directive to the assembler. It tells the assembler that the execution of the program should start from location 0. That means location counter will have to be initialized to 0 to execute this code. So first instruction will be in 0. It also tells that John is the name of this program. The assembler has to do some task. Assembler will have to initialize the location counter value to 0. Now, What about load 1 and VAL2? Here, load 1 VAL2. 1, these 1 and 1, they indicates the names of registers, scratch pads. VAL, as a name indicates, it can be, it is a identifier where some value is stored. So right from our programming days, see, when this should be in you, it should be glued to your mind. When you write a program in high-level language, when you use a variable, it is a place in the primary memory. Mind that. Whether it's a structure, let it be a class, let it be a variable, let it be a bitwise operation. See, everything we play with the memory. Now, we have also learned about memory hierarchy in a machine. What is meant by that? Even if the function of memory is same, to store, if they vary in performance. Say the memory registers available in CPU are the fastest. They take nil time. Their speed can match with speed of CPU. Later, when you go to primary memory, there is some time involved. When you go to secondary memory, the time is still greater. So due to this, why this memory hierarchy comes? It is because of the cost. Even if the technology is advanced till today, the cost of building high-speed memory is still a nightmare for hardware designers. That is why we have a limited amount of RAM and registers in a machine architecture. How the research have advanced in this space? The concept of cache memory was introduced. Varying levels of caches, level 1 cache, level 2 cache, like that. So registers are fastest memory pieces on a motherboard. So value 2 represents again a place in primary memory. So here this load instruction, it takes the value stored in address VAL2 to 1. See this. Now, can you imagine the corresponding higher level CPP instruction? I gave you a hint like in B square minus 4AC. Suppose that you say y is equal to x plus 1. Y equal to x plus 1. What will happen? X is a memory location, like VAL2. Y is a memory location like VAL2. Now, what is happening there? Y equal to x plus 1. That means the system has to check what is the value that is stored at address X. That value should be taken and it should be stored somewhere. See loading. That value should be taken. It should be loaded to a register. That is load. Then the value is stored in 1. Then 1 can be incremented to the value in 1. That is x plus 1. After that, the value that is add 1 VAC adding. After that, what will happen? Then later the value should be stored back to y. So again from the GPR, value is to be stored back. So that is why y equal to x plus 1 will be translated by the compiler. In high level language, remember that in high level language, we'll be having only one statement. Our one statement will be bifurcated to a set of statements when the actual machine code is generated. That is how assembler and compiler works. Now, the second instruction is a load instruction. Meaning of load is given here. Load the value stored in variable VAL2 into register 1. And this, I hope that you know about GPRs, general purpose registers in a machine, accumulator, register B, register C, register D. So the exact name and nomenclature, it varies from machine to machine. But all these are commonly called as GPRs. So 1 is a GPR. Again, add 1 VAL1. What's happening? Value stored in VAL1 will be accessed, and that value is added with the contents of R1, register 1. That means now we have added the value of V2 with V1 in these two. Then we are storing back the result to RES, store 1 RES. Store the contents of 1 to the next memory location. So this is how we interpret these three instructions. Now, why the location counter is initialized? Because each of these instructions will have to be accessed. So suppose that the first instruction is this load. After load, the next instruction is to be taken. Suppose that the first instruction is at address 0. Then what is the address of this instruction? You will add 0 with the length of this instruction. Length. So every instruction will be having a length, and this length will be known to the assembler so that it can add that to the value of the initial value of LC, then the next instruction can be accessed. And that is the importance of this start 0 instruction. Now you might have noted that. So this is a pseudo instruction, whereas load, add, and store are called as machine opcodes. Now, what about these data directives? You can see 3 data directives, and we have 3 variables here: VAL2, VAL1, and RES. That means they contain how these data values are to be manipulated. So 4, 5, and 1 are to be stored in these values, and this is how it is being specified here. So this is how a assembly language program look like. Now we have to understand what an assembler has to do when it is getting translated to a machine code.